Hi, welcome to this video. It's a demonstration on the NSX Advanced Load Balancer, also called AVI Networks. And in this particular situation, I'm going to be taking you through AVI for Openshift container platform. Just to set the scene here on what AVI sets out to solve. If we have a look at these old generation load balancers, a familiar legacy approach here, we have the all too familiar active standby pair arrangement, and of course lightly loaded active standby, typically sitting there inactive waiting for failure. We have these load balancers deployed across different data centers, different lines of business, different security domains, and of course when it comes time to deploy load balancing services for applications, quite often load balancers for specific use cases as well. Pretty soon we have lots of load balancers to deal with. And that really poses challenges around capacity management. How do we fair and equitably use the available capacity, considering we've paid money for licensing, CPU and memory of the device, or CPU and memory of the virtual edition device to have it sit there idle? And how do we plan for peak workloads and growth of a platform? Secondly is around having monolithic appliance-based or virtual edition-based devices. The control points are separate. Managing various control points is challenging, keeping in mind that we need to have the configuration exactly right. And then, of course, when something goes wrong in the network, all too often with this fragmented solution, how do we then pinpoint problems? And we all know from a networking standpoint, TCP dumps and packet captures and Wiresharks are unfortunately where a lot of people have to go with this. And then having a fragmented fleet of load balancers poses the perennial question around upgrading and the continual cycle around impacting services when load balancers invariably need to be upgraded for patches and hot fixes and lifecycle management events as well. And then if you consider this legacy architecture against all the modern advances in multi-cloud usage, and in particular, how does any of this support the containerized platforms as well as virtual machines? And then giving modern day based services approach to like load balancer as a service, multi-tenancy. How do you carve any of this architecture up in a cloud-like manner to provide elasticity and scalability? So it's these challenges that AVI has traditionally set out to solve with its load balancer. So what we've done architecturally is quite different. We've split the monolithic based, appliance based approach into two parts and separated the control and the data plane a la SDN style into two. So here we have a centralized control plane, which is not only a central point of configuration but also a central point of orchestration, which we'll talk about in a moment. And then this indiscriminate cattle class, if you will, data plane that gets instantiated where and when the load balancing is needed in various environments, whether that be on-prem or in AWS or Azure, public clouds, container platforms, etc. And what we end up with out of the virtue of this unique architecture is some very, very modern characteristics to load balancing, and that's central point of orchestration, the ability to then have load balancing service as an elastic application fabric in an active-active or even an active-active-active fashion. And that lends itself to scale-out conditions, cloud-like behaviors, and also zero impact lifecycle management events, all centrally driven from a controller. One of the big benefits of separating the control plane from the data plane is that the data plane is now free just to handle packets, do the SSL offload, and also feed the control plane upwards of 500 data points of how the application health and how the transactions are unfolding. And the control plane is now free to be a big data analytics engine and provide lots of visibility and rich analytics and telemetry about how our applications are behaving. The control and data plane can be very easily carved out into tenancies. So it's very easy to achieve utility models and cloud-like models with load balancing as a service, etc. And of course, our UI, our API first approach means that you can very easily automate AVI out of the box with lots of cloud connector automation. That could be things like automating vCenter, NSXT, Route 53, AWS. All that stuff is AVI is cognizant of the environment that it's been deployed into, and therefore can orchestrate a lot of the day-to-day tasks like IPAM and DNS, etc., that are very necessary for the load balancing to occur, as well as this northbound intent and taking a declarative outcome based from Terraform or Ansible or even VMware's very own vRealize automation. So all these modern characteristics, by virtue of our software-based architecture, sit across the bottom here. Areas of orchestration, elasticity, the resilience and automation, all driven from a cloud-based, SaaS-based service. And then, of course, the core pillars of functions that we provide from our REST API, and of course our UI as well, local traffic management, global traffic management, a whole raft of application security, denial of service protections, all the way up to and including web application firewall, and of course load balancing services and secure container ingress services for various container platforms such as VMware's Tanzu and of course Red Hat's Openshift, to name a few. All wrapped up in analytics and observability so we can gain really key insights into the application or user or security behaviors of our applications, and troubleshoot very quickly as well. So let's switch gears here and have a look at the typical deployment for Openshift and explain some of the areas of consideration as to what AVI goes to solve in this particular domain. With a typical Openshift deployment architecture, you end up essentially with multiple tiers of load balancing, which aren't always integrated. If you consider a single Openshift cluster, pictured here on the left, by default it ships with HA proxy doing the load balancing, or router Ingress. Could also be Nginx for that matter as well. But they're objects that sit inside the cluster. So we need to load balance this stuff into the cluster for those objects that are actually being exposed. So from outside the cluster, we have another layer of load balancing, and typically that's something like a local traffic type load balancer. And then again, if we expand that cluster over to another part of the data center or another site, now we have this internal load balancing, the external load balancing that's required when you run MultiCluster OpenShift, despite having HA proxy anyway, all outside of the OpenShift space. Now, the external load balancing is not terribly aware of the OpenShift services. They're quite often ships in the night and no integration. And now, to stitch all that together, you need another layer to do the GSLB functions as well. So that's a lot of points of configuration. There's a lot of areas to, to integrate together. Sometimes these are static integrations without them being necessarily transitive around the application status or the health. And if you consider DNS, customers also end up needing to use something like wildcard DNS for all their applications. And wildcard DNS has no granular policy like restricting users or just publishing only the deployed services. And if you're not using wildcard DNS, the DNS updates that you need to make are out of band and also really challenging once ingresses keep getting deployed or recreated. You need to have the matching DNS entries, and that's quite painful if you don't have that part of the equation automated as well. And of course, the performance of the OpenShift router by default is HA proxy, and sometimes customers see that as lacking. So the holistic solution here really isn't reacting to the actual live health of the pods themselves all the way through in a transitive manner. So these really manifest into four main challenge areas here that AVI goes and sets out to solve. And that's really around these four pillars on the right, discrete solutions, complex operations, lack of observability, and this oxymoron that is partial automation. So what is AVI able to deliver in bringing all these moving parts together? Well, we can collapse the GSLB, the WAF, the Ingress, the DNS, the IPAM, all into an integrated system across multi-tier or multi-availability zone load balancing. So that can be multi-cluster across 2 data centers or even into public cloud as well. And we can deliver the L4 and L7 load balancing objects that you may require. Not only does this reduce the amount of layers that the traffic needs to converse and optimizes the actual packet path for the LB and the client to talk into the pod direct, but also collapses the amount of layers that you need to operate. And we give you the analytics that AVI is able to provide for VMs, public cloud, and containers all alike. So before we step through the demonstration, I'll give you an idea of what's to come with the demo. So we'll be deploying an e-commerce shopping application into the Openshift clusters. Then we'll expose that with an L4 object of service type load balancer. And then as we build the application, we'll start to see AVI automatically react to that. So secondly, we'll protect the application. We'll deploy secured TLS-based ingress or routes, as Openshift calls them. And then we'll introduce advanced concepts like turning on the WAF, turning on rich analytics, all just through YAML. And that will really lock down the north-south entry into the app that exists into the clusters. We'll move inside the cluster. We'll be showing the stuff around east-west traffic controls, things like network policy and how we augment the default Kubernetes network policy with Antrea as a CNI and do a much more sophisticated Antrea cluster-wide network policy or Antrea network policy. And all this could be driven from NSXT, from the management plane integration of NSXT. And after that, we'll deploy another application specifically to demonstrate multi-site or cluster services across multiple clusters. And this will invoke things like GSLB, and we'll see how we can very easily allow our developers to manipulate GSLB outcomes, allow them to instantiate GSLB records automatically just through regular app deployments. So our lab topology looks like this. We have a multi-cluster scenario, as you can see here. Now in my instance, for resource saving, I'm just deploying this stuff on a single management network with a single AVI controller and a single vCenter. But this is akin to having, unique cluster endpoints anyway. So I've got actually 2 discrete Openshift or OCP clusters here, OCP1 and OCP2. So the net effect of me deploying applications here, I do have discrete clusters, which simulates all the concepts that I've just been through, despite it being in a collapsed architecture. Firstly, we'll deploy a shopping cart app, the famous Google microservices app. And this will provide a service, an L4, an L7 route. We'll do a WAF there, just in container cluster 1. And these will be our FQDNs that will have AVI automatically publish. Now we have a subdomain of OCP01 and OCP02 already delegated to my corporate Microsoft DNS, which pushes into the DNS bits inside of AVI. So that makes AVI authoritative for these DNS subdomains, and then we can drive the complete DNS outcome in concert with all the Kubernetes deployments. So no wildcard DNSing required. It just gets deployed. The A records all get created as the apps are created and deleted as the apps get deleted as well. And secondly, we'll deploy the same instance of a Hello app across 2 different container clusters. And here we'll be able to reach each cluster individually by their very own unique FQDN, but also we'll be able to then reach a GSLB record, which will then essentially be like smart DNS and automatically select an available site based on certain criteria. Right, so let's kick off. So I have 2 OpenShift clusters, OCP1 and OCP2, and they've been aliased as K1 and K2. And I can show you here in cluster 1, you can have a look at the nodes that exist there. You notice that that's TVN2P denotation. And in cluster 2, likewise, we have another unique cluster, 3 masters and 3 worker nodes there. If we have a look at what that looks like within vCenter, these clusters have been deployed as virtual machines, and you can see them reflected in vCenter exactly the same there. Now, if we have a look at some of the pods running, we'll just go back to cluster 1 and have a look at some of the pods, and you'll notice some very, very typical namespaces that you would expect to see in Openshift. So they are live and up and running. Now, if we have a look at some bits and pieces that I've injected into my container clusters, you can see here that we're running Antrea. So when I've deployed these OpenShift clusters, I've selected Antrea as the CNI of choice. So I can do some more sophisticated security policy. I can do tiered policy, negate statements. I can do RBAC against different portions of the policy, allow DevSecOps and allow maybe security ops to manipulate a certain part of the policy and developers to only manipulate another portion of the policy. Sort of like imposing guardrails on policy. So I have Antrea running, and you can see there that it's an operator and an agent-based architecture. So each element in the cluster, each node, worker node or master node in the cluster has an agent that's running as well. And for reference, for those that haven't heard about Antrea, Antrea is a Kubernetes native project that implements the CNI and the kube network policy. So it's OVS based, and it has a number of benefits over the native security policies, as I've mentioned. Being able to do, say, cluster wide policy, tenant isolation for highly secured environments, tiered policy models, priority evaluation. And these are things that you would come to expect out of a firewall, right? To do proper rule-based evaluation. But one of the things you can do, and I'll show you in a moment, is drive all these policies directly from the NSX distributed firewall UI, which is a big simplification for a lot of customers that find Kubernetes network policy complicated, but yet want traditional sort of network or security engineers to be able to partake in that policy, or at least govern and drive moves, adds and changes, etc. The other aspect to these clusters is that I've deployed the AVI Kubernetes operator that you can see right there. I'll just expand this window over so we're not truncating. And that's a little operator that runs inside the cluster. It's a control plane function only, and it sits there and listens to all the calls that are being made into the Kubernetes API server and hence into the etcd database. So whenever there's load balancing things that have been described in YAML, say from a Kubernetes deployment, AKO will translate those calls into the right API calls to go into the AVI orchestrator. Now, AKO kind of looks like this. If we look at it from a slide perspective, we have a given Kubernetes cluster or an OpenShift cluster, and that's that little AKO pod that I was just showing. And each cluster has its own AKO pod running and listening for its own respective calls in Kubernetes. And when it becomes time to drive GSLB outcomes across multiple clusters, that's when we'll then go and use the AVI MultiCluster Kubernetes operator, or AMKO as it's called as well. And at all times, our AVI service engines sit outside these Kubernetes clusters for maximum performance, so we're not having to traverse within a cluster. So the AVI service engines will be able to then listen to those calls. The orchestrator will listen to those calls, and the orchestrator will drive the service engines to have the right connectivity, the right TLS, the right packet handling behaviors, and then direct the traffic into the exposed worker node and port combinations, and more on that in a moment. So if we go into the AVI controller now and we have a look at how it's set up, if we take a look in some of our infrastructure setups, we have this notion of clouds here. You can see various clouds that we can set up in AVI. And really these are cloud connectors, and it's AVI's inbuilt out-of-the-box automation capabilities to be able to run in various environments. Linux server is us commandeering a bare metal server. AWS, vCenter for VCF deployments. For customers that have that and or NSXT, we can also integrate with vCenter and NSXT to have full automation onto NSX logical segments and be able to then automatically drive the DFW exclusion list through the pinholes and source noting that is dynamically needed for the service engines as well. And of course, there's other public cloud offerings here. So with that, we have various service engines that have been deployed. You can see my service engines are running there, and not surprisingly, you'll see that those as OVAs or virtual machines that are sitting in my vCenter environment as well. Notably, there's a service engine group that consists of 2 service engines for my OCP01 and conversely for OCP02. And then, of course, I've got a DNS-only service engine that's handling all my DNS traffic, auto-publishing FQDN records into A records and C names, etc. through that particular OVA there. And you can see the service engine groups, and that's how we manipulate the high availability and resiliency characteristics, the resource characteristics as well of the service engines. If we have a look at the IPAM profiles that I do have set up, you can see here that AVI has been told to be authority for some domains here, OCP01 and OCP02. And in terms of IPAM, we are going to be handing out on particular segments here, and this is where most of my VIPs will end up. AVI has been told to then auto-allocate from a pool of addresses that I've chosen. So the DNS, the automatic IP assignment, should come automatically as the YAML flies out of Kubernetes and AVI does its thing against. So just a quick view of some of those analytics. I'll jump to another demonstration lab here real quick because it has a lot of colorful traffic being simulated to demonstrate some good stuff here. If we have a look at a particular application called AVI demo that's been deployed, straight away you can start to see the way that AVI will render the application, and not specifically it's an infrastructure view or a load balancing view first and foremost. It's showing you an application and the application's health, which is quite nuanced. It's not up or down. It's given a health score out of 100, and you can see here, in my particular application here, there's a resource penalty of -4 and a security penalty of -20. So the AVI is scoring these application healths based on things like CPU memory of the backend servers, how healthy is the site behaving, are there any anomalous behaviors in the application? My load balancing might be health checking fine and it's up, but it's severely different from what it was last Tuesday as an anomaly. And of course, I might be using substandard, ciphers or TLS versions, etc. If we dig into my specific application now, we can have a look and see lots of analytics that AVI's collected out of the application health. And if I look now over the last day, we can start to see some quite, straight away we can see some anomalous sort of behaviors on the graph. If I mouse overing this, AVI is doing, chronological timing. It's being a TCP proxy, so it's being able to measure the application health in various ways. So it's taking 18 milliseconds for the client to connect to the load balancer, 2 milliseconds to get to the backend server. The app takes 20 milliseconds to generate content, and then the transfer takes 10 milliseconds to get back. So overall, our application is taking around 50 milliseconds to respond. And that's averaged over the last day. And I can dig in here and use this type of forensic application health to really look at the application performance, but also troubleshoot the application as well. And I can see here there's been some quite marked irregularities in, say, every sort of 6 hours or so. If we dig into those logs here, and then I can have a look and say, these are the significant logs over the last day. If I change this to the last, say, 6 hours, I'm now looking at the AVI log system, and this is pretty much like a network DVR. I'm looking back in time now without the need to do any packet captures, without the need to do any TCP dumps. I can look back at my application and see how it's been behaving. And if I change that view back to the past day, let's filter now. We know the application response time was getting a little bit unruly, over 100 milliseconds. Now I can quite easily just filter out the logs and only show the logs where the application took more than 100 milliseconds to respond. And now we're starting to see some pretty obvious behaviors on this graph that we sort of saw in that end-to-end overall timing graph. We can mine this data very easily now. What are the browsers involved? what are the client OSs involved, what locality are all these. So mind you, I'm only looking at these problematic logs now, and I'm looking for common patterns in behavior. So they all come back to a mix of those two service engines. What is the URI path that these problematic logs have been generated from? Yeah, nothing telling here. It seems to be quite a mix. But if I have a look at the backend server address here now, pretty quickly you can see that 99.99% of all my troubles have come from one particular backend server that's causing this. And if we go back to the overall tree view of my application and blow that back out again, the server ending in 101 here, 100 is down, but it's not actually causing those particular behaviors. It was actually this guy here, this 202, as you saw from those logs, and it's actually up, by the way. So going back to those logs real quick, we can very easily see that which application server was causing all the issues. So very instantly we know that it's not a network issue. We can go and point this trouble ticket back to a server team to go and fix the application logs. And in this particular instance, there's a cron job running on the one particular backend server that's causing it to respond in an untimely manner. Now, digging into those particular transactions, we can see a whole bunch of information about the client, about what's happening on the virtual server, the source natting coming off the service engine, why AVI deemed this to be a significant log, and then even all the way into the request headers going to the application and the response headers coming from the application. So there's a wealth of information that we can glean from this without ever having to touch a load balancer or do a Wireshark or a TCP dump. Quite powerful troubleshooting capabilities as well. So let's cancel off that and let's get back into our Openshift demo. And let's start to then have a look at some of the applications that I've got to deploy to see how this all fits together. So if I come into my jump host here, you'll start to see I've got some various files that I'll deploy. Now here, let's have a look at the shopping cart. Oh, this is the shopping application that we're going to deploy. But in particular, I'll just show you the front end because that's really where the load balancing is getting it done. So you can see here that I'm just about to deploy a complete application here with a cluster, a front end service. There's a number of services in this application, but the front end service will be fronted by a server type load balancer right here, and AVI is going to automatically send load balancing into this particular service. So let's apply that now, and you'll notice that my virtual services will now jump up to it's 27, but it's as these applications are deployed, AVI will create load balancing for that, and you can start to see that now it's jumped up to 28. And I've only created an L4 object here, and that's what's been created just here. So in cluster 1, I've deployed the shopping cart app. And if we just come over to this particular tab, now you'll see that it's an L4 object. It's just a HTTP URL. The application's coming up now because you can start to see that the front end's up available, but some of the other services that are involved aren't quite ready, but yes, now they are. So there's quite a bit to that application, and I'll give you a quick look at what's been deployed. So a number of deployments have in turn created a number of replica sets, in turn have created a number of pods. Now the front end service, which I showed you in that YAML, has been deployed, but also the service type load balancer has been deployed to front end that as well. And you can see the external IP as being called out as 137.173. If we jump into AVI and have a look at that, here we are, 10.174.135.173. So there's our layer 4 load balancing object to support the shopping cart application. We can have a look at some extra things about the service that AVI has deployed. There's our VIP address that's been deployed. And there's some notations here that I'm going to explain in just a moment. If we have a look at the pods that are running, you can see that they are being deployed into cluster 1, and they're probably on a mix of one of the 3 worker nodes that are running there. But this application now that's been deployed has, implicitly, from me just deploying it via that YAML, has automatically got a VIP address, which I showed you. It's automatically created a DNS entry in its subdomain that it's authority for, hence that I can call this application straight away via its FQDN. And the port groups that the service engines are connected to may well have already been pre-configured, or AVI will drive the port group attachment as courtesy of the vCenter Cloud integration as well. So there's a lot of things that have just been implicitly automated just with me deploying that particular application here while that application has been deployed. You'll notice in AVI, you can see that front end cluster IP service has been fronted by a service load balancer, and we're hitting, without any static routes or without any node ports even, we've been able to directly hit a worker node and a port combination here. And that's exactly what this notation is in this. If I describe the pod for the front end, you can see there's a node port local notation. So we can go directly to the worker node and directly to the port. And that's courtesy of a feature called node port local. Now I'll describe the ways that we can connect to the container pods on the back end here. So the first method is just the default cluster IP. Obviously, cluster IP is an internal address that's only known within the cluster. So a load balancer has to then take that and expose that and send into the cluster. Now, commonly this is a non-routable IP, and you can see that in this slide here, it describes AVI needing a recursive static route for the hidden cluster service ranges as well. So this can happen automatically. We can choose to use this mode. AMKO will still automatically configure the static routes, which is nice. It maps the pod siders to the corresponding node IPs. The load balancing pool will still have the pod IPs as members. The service engines can health monitor the pods directly, which is great. And we can still provide things like persistence, but the pod sider here isn't directly reachable. So some people don't like that as an approach, and they may choose to deploy their services as node port. And this is obviously another famous way to deploy or expose services in Kubernetes. And here we get the convenience of being able to route directly to the pod sider, but because we have to go through kubeproxy, you can see here all Ingress is via the kubeproxy, and then it has the IP tables read out of where the actual pods need to be, or where they need to be load balanced to. You lose the ability to do the health checking for each individual health of each pod, which is not great. You'll just see a single pod, even though you've scaled out your front end to like 10 container pods as well. So, begs the question, wouldn't it be nice if we could have the best of both worlds? And that's what is unique in the market with AVI and the way it works with Antrea. So this is node port local, and it's one of the nice features of the Antrea CNI, which is the default CNI in Tanzu and a lot of other third-party container platforms as well. And here we have it all: direct pod connectivity, not needing to use static routes, and each pod is a different node port, as you saw in that annotation. So we don't need to use kubeproxy here. So we can health check every pod directly. We can have persistence to the individual pods. It's very nice indeed. So that's what we're describing here with this node port local, and you can see there's no static routes. We're hitting the worker node directly. That's the actual routable address of the worker node, and that's the pod that it's been exposed onto. Look, if we scale up our front end now to have, instead of one front end pod, we've changed the replica set to have 3 pods. I can go and describe again the node port local annotation, and you can see now the pod replicas have been strafed over 3 worker nodes, and each having their individual node ports and the UI is now reflecting that exactly as well. And then if we have a look at the endpoints that's using, yeah, you can see the front end now is strafed over 3. It's been scaled up to 3 pods. So that's how we're getting into the cluster for each of those front end pods, and that's the resultant, you know, CNI CIDR ranges that go onto the back end as well. So let's have a look at how that fits together in terms of configuration with regard to AKO. So if we have a look at this config map, and this is one of the few things you need to configure for AKO, you can see here in this config map here, this can be a global config map that you've deployed, or this could be particular to each AKO that you deployed in various clusters. You can see that I've defined the service type. Instead of node port, I've put node port local. Yeah, that's my VIP address that you've seen me deploy into. And I've made this the default Ingress controller, so I can use Ingress classes indiscriminately. And my CNI plugin, I've told AVI that I'm using Entreya, just like I told Openshift when I did the API install of Openshift 4.10 that I'm using Entreya as well. So let's scale that. Let's get out of that, and I'll scale that front end back to just one node. You can see if I get the endpoints command, you'll see that front end has gone back to just a single pod. And if I have a look at the node port, we've only got, you know, a single pod representing the front end as well, and the UI reflects that. Now let's go a little bit further with this application. Let's have a look. We'll put a secure ingress route on the same application that's already been deployed. I'm going to publish this route, this Openshift route, to this URL. It's going to have a backend target of 8080. So let's do that. We've got 28 services, virtual services configured in AVI. Now let's put an Openshift route on that application as well. And let's have a look and see. Let's describe that now that it's been deployed. You can see there's been some TLS certificates that I've supplied, a private key and the cert. It's going to be an edge route in terms of Openshift non-clementure. And you can see here it's been deployed. This is the FQDN that it's listening on. Again, this subdomain has already been delegated, so that's going to send the DNS request into my AVI DNS, which is fully automated against this deployment. And now you can see that the virtual services are 29. This is my application here. And now I should be able to, all going well, go to this HTTPS URL. Yeah, it's already refreshed. So now I have a TLS secured ingress, so an L7 ingress now into the same application that's running. So I can go into buy a watch, place the order. I've triggered off some traffic. Now if I go back and have a look at that application, it's a very newly deployed application. If I go into the logs and have a look, yes, there's some activity. You can see my client IP, but you can see these are my transactions that I just literally did in this tab here. Yeah, a whole bunch of like client information. You can see that I've come in to the virtual service here. It's been source natted, and you can see the timings, etc. So I guess if we pause here and have a look again, AVI has assigned, if I look at the virtual service here and hover over it, go back to this, the newly deployed route. If I hover over it, you can see that the virtual service has been given 135.180. So you can see with this deployment that AVI has, again assigned the IPAM, auto-published the DNS records, driven vCenter. And, if I wanted to then, take an application and scale it out, I could push this across multiple service engines as well, or the service engine group could already define that behavior as well. Now, going even further, I can have a look at doing some extra stuff to this application. So already it's now a secure TLS-based application, but using some of the custom resource definitions or CRDs that AVI makes available with AKO and AMKO, I can now quite simply, for this particular virtual host in OCP1, the application I just deployed, I'm going to actually turn on a system WAF policy. Now this could be a very customized WAF policy, or it could just be the system WAF policy. And I'm actually going to turn on the analytics profile, because you'll notice here that there's no significant logs available for consumption here. So quite easily, I can just deploy that YAML against the Kubernetes cluster, and pretty soon you'll be able to see that that very same application now has a shield logo on it, denoting that it's been protected with the WAF. And if I go into that application once again and go into some of these logs, you'll see now that non-significant logs are available for consumption. So non-significant logs are pretty much just all the boring logs that have been healthy and successful, rather than what AVI is deeming significant. Significant is what what we think that you should take a look at because they're abnormal or there's been an error, etc. So I'll just generate some traffic there, jump back to AVI, and you'll see that now there's a whole bunch of like non-significant logs. There's things that HTTP 200 transactions being successful, and all this stuff here is my client IP. So you can see here, this is me clicking around, looking at various products in the store. Now that WAF's been on, a common ask is like, well, okay, how much delay has the WAF incurred on my application? Well, you can see here a lot of this stuff has been bypassed through WAF because of the policy definition. But there's the WAF in itself gives you an end-to-end timing also that. In this particular instance, that some of the WAF logic to process was 0.193 milliseconds. So you can get a pretty clear idea of if the WAF has been involved and how long it took to do its thing as part of the packet processing path. Okay, so now that we've exposed and protected the app from a north-south perspective, what we're going to do now is secure the east-west of this entire cluster as well. And I did mention that I've deployed Entreya into this cluster. If I can type, and you can see again it's a client server type arrangement where we've got an operator running, and then we've got a whole bunch of agents out there on the worker nodes. And that application that I did deploy obviously has some labels attached to the pods. If we go and have a look at the Redis cart, for example, the app equals Redis cart, so there's a particular label that's already there. And if we jump over to NSX now, you can see that as part of the NSX and Entreya integration, we can now consume that cluster. So there's all OCP01 cluster, and we're consuming all the things out of that: nodes, pods, services, etc. Namespaces, cluster network policies, which I've derived. But then if we go and have a look at the security policy now, I can now describe cluster-wide security policy or namespace-wide security policy in NSX that then affects that CNI. So you can see here in my Redis cart, I've defined the Redis cart as matching on that discovered label. So Kubernetes app discovered label app equals Redis cart. So it gives us the ability now to then look at, if I look at some of these groups that pertain to Kubernetes objects, if I find the Redis cart real quick, here it is, Redis pod. We're now able to, you'll see that the policy is an Entreya policy, and the criteria is we can now use these selectors to define security policy. So this is not anything that you couldn't already do inside of Kubernetes, but now we're using the enhanced security capabilities of Entreya, and the Entreya objects now integrate into NSX. So you can now just use your distributed firewall constructs to VMs, to containers, to containers, to containers alike. So it's quite an easy way to then drive the security policy. So maybe the developers use YAML and there's version control around network policy, but yet there's tiers of things that people can and can't control. And network security folk can still see the policy and drive the policy this way as well. And you can see some of the constructs that we can match on now in the distributed firewall. We can match on pods and on Kubernetes services, on namespaces, etc. And I've actually written a policy that fits that shopping cart application, and that's exactly what you can see here is all the bits, all the pods that have been spawned from replica sets going back and forward. Now, interestingly, I can show you the Entrea cluster network policy, and you can see here that there's a number of things that it's rendered in Kubernetes, and that's all the policy that's been defined here. Now, you can see if I go in here and just put another CIDR range in this address, and we'll do 32.32.33/32, just to show you a change. So driving the policy directly from the NSX DFW here results in it's a bit quick there, but there you can see my brand new CIDR entry. And all the things above it are all the Redis pods, the AB service cart pods that I've defined already. That's just a very simple change to show you that, affecting the policy here drives the cluster network policy inside of NSX as well. Okay, so let's switch gears a little bit now and show you some of the multi-cluster capabilities of AVI. So we'll jump back to AVI and we'll show you now, we'll invoke the AVI multi-cluster Kubernetes operator. So that's the AMKO that I showed you earlier, and you can see that it's running in each of the two Red Hat Openshift clusters. I already have a GSLB infrastructure set up in AVI. So you can see here under GSLB and AVI, I have a subdomain that's been delegated. So that's going to be my GSLB record subdomain. And then if I had 3, 4, 5, active participant GSLB sites, they'd all feature here. Now, because I'm using collapsed architecture, there's only one site here, but it all works the same. So I've chosen to GSLB between two clusters at one site. But this could very easily apply to 2 clusters across 2 sites, or even 5 clusters across 5 data centers. So another outside of using AVI, normally once an Ingress gets installed, you may well have to use a wildcard entry for DNS or manual configuration, as I described earlier, each time a service is published, or even automate that out of band, which is quite awkward. But with AVI, when we deploy services at the L4 or L7, and we indicate that we need them to be GSLB, AVI will then auto program its DNS to publish these records across the various places we've pushed the application, whether that be cluster 1 and or cluster 2. So let's have a look now and have a look at how this is configured inside of AVI, and you'll notice there's some CRD defined objects. This is GSLB config here, and if we look a little bit deeper into this little object, you'll see some of the bits of configuration here, and this is where I'm defining my clusters that will participate in GSLB. I'm saying that I want to have cluster 1 and cluster 2 be part of this GSLB domain, and I'm also saying I want to use custom global FQDNs because I want to define unique URLs for each of the app instances in each cluster. But then I want to tie it all together with a common GSLB FQDN domain as well. The other point of configuration is this guy here, which is our global deployment profile for AVI, for GSLB. And if we do a little describe on that, you'll see now that I've defined, again, the clusters that will match in these notations. And I'm going to use an app selector so we can pick up which particular applications are going to be part of this whole particular GSLB configuration. You can see here the label of app equals GSLB is the one I'm going to use today. Now if we have a look at, I'm just about to deploy my Hello app here. I'll get into the right app directory. But if I show you just the snippets of the deployment YAML here, I'm going to deploy a service and I'm going to do a deployment. I'm going to create an OpenShift route. But here is the tie-in with that app selector as part of the GSLB. So I'm going to put app is GSLB selector there, and that way AVI will know to pick it up and GSLB it accordingly. And if I just show you some of that YAML in its entirety, we have a service being deployed. It's going to be in cluster IP, but node port local, of course. We'll expose it the way that I showed earlier. We'll have a deployment, and we'll have the actual container is a Hello Kubernetes container. But for each of the instantiations of it in each cluster, we're going to have a message that describes it as to which cluster it's coming from, so we know where our GSLB is heading. And then, of course, the Openshift route, that is very similar to what I deployed in that previous shopping cart app. And then the GSLB host rules, and this is where I can define my global FQDN for this particular service, and then the unique FQDN for the app as well. All right, let's have a look at the other deployment YAML, and you can see here there's a message for OCP1, there's a message for OCP2. They each have their own respective unique FQDNs, and then we're going to tie the FQDNs together, just like we showed in this diagram here. So we're now deploying the yellow application. Unique FQDN there, unique FQDN there, and then a common GSLB record there as well. So before we do that, let's just query that GSLB record. It's not active, so of course that's not returning anything. So I'm going to put a loop on here to always query the GSLB record, so we can see where AVI is pointing that GSLB record into particular the application. So let's deploy the application now, and you'll see that the number of applications in AVI will go up from 29, should bump up to 30. You can see it there, just like we described earlier. There's been a deployment, a replica set, a service, 3 pods out as a result of that, and an Openshift route. And if we jump back to our GSLB services now, you can see that our GSLB record has now been created because of that deployment. Hello GSLB, OCP VCN lab. And my dig against that is now starting to work for that particular application. So if we go back and have a look at the app now, the Hello app, I can filter on it here. You can see that my VIP address is 182, and that's exactly what the GSLB record is returning here, 182. So we have an application that's up in cluster 1 and it's working, and we've GSLB'd it, and all is good. So now let's go and deploy the same application in cluster 2, and you can see again in cluster 2 exactly the same objects have been created. But this time with a different FQDN. So now I can go, there's my application in OCP01. I should be able to now go directly to that application in OCP02. And my FQDN record, hello GSLB, which references neither location, is currently being sent to OCP01. And you can see here that 182 is still being handed out by my GSLB service. As the service in cluster 2 becomes initializes and is coming up, we should start to see our GSLB record now handing out A records for the second cluster, which is 191. You can see here now there's 2 A records being handed out for that GSLB domain. And if we go into the Hello app for OCP02, it's the 191 that you can see right there. So now we have a mix of records being handed out. We're sort of 50-50ing our traffic, or round robining our traffic to one cluster and then the other cluster. This is just a very simple round robin based on priority, but we could do something very sophisticated around geolocation, which is very common for customers as well. So what I want to do now is just scale out ahead of time and do a scale out event to show you that scale out is completely automated. AVI could scale out accordingly based on certain triggers. The connectivity to the scaled out worker nodes is completely automatic. So here I have the 3 worker nodes in cluster 2. I'm going to now change the machine set and scale that out to 10 worker nodes. So we should start to see some activity in vCenter. You can see that the OCP02 is now scaling out. There's a whole bunch of virtual machines being cloned and created. If we go into the Openshift UI for the cluster, you will see that now there's the machine set is now 10. We'll start to see some worker nodes, or soon to be, some worker nodes will be spun up. They're not really ready yet, they're being created. And then if we have a look, we can track that over in Kubernetes and have a look at the nodes. You can see there's only 3 worker nodes there yet, still early days, but let's leave that. We'll come back to that scale out event. And now we'll have a look at, we'll go back to our Hello app, and we know that we're reaching it via an FQDN. And currently we're using a 50-50 approach. So here's the GSLB host rule. This is another CID where we can manipulate GSLB behaviors. And I'm doing a traffic split of 1-to-1. Obviously my TTL is fast, so I can do that dig. But you can see here that's a pretty even mix. It bounces between 182 and 191. So it's fairly handing out my 2 clusters equally. And that's fairly obvious to see. What if I wanted to then have a look at, I want to have cluster 2 take a lot more of the load. So I've just scaled up all the Openshift worker nodes. And now I want to have, but ahead of me scaling up the front end of my application in cluster 2, I want to send, 4 times as much traffic to cluster 2. So now I can manipulate via this host rule for this FQDN record, a weightage of 4 versus a weightage of 1 on cluster 1. So if I apply that now, all from Kubernetes, we've manipulated, the use of the clusters, if you will. So we should start to see a 4-to-1 sort of representation of these digs going to, cluster 1 and cluster 2 respectively. If I just see what cluster I go to coincidentally on that FQDN record, it's now punted me to cluster 2, as you can see there with that pod. So it's probably going to push me to cluster 2 quite a bit. And you can start to see here the FQDNs that are being returned. So there's not much of cluster OCP01 being returned. It's mostly cluster 2 because of the 80-20 weightage. So let's see what happens when we delete the app out of cluster 1 completely. So now the whole Hello app has been blown away from cluster 1. That simulates a data center 1 failure. And not expectedly, you'll start to see that just cluster 2 is being returned by the GSLB record. And if we jump into that GSLB record and have a little look at what's been automatically programmed by AMKO, you'll see now that there's really only one endpoint in the GSLB pool, and that's OCP02. So there's no one OCP01 that's been removed because the service has been deleted. And you'll only ever see cluster 2 being returned for FQDN. So the clients will now be steered into cluster 2 accordingly. So let's bring that application back. And if we go into that GSLB pool and show you that again, you'll now see that OCP1 is there and OCP2. So now we're back in business with 2 data centers basically. Okay, so I scaled out the Openshift clusters. You can start to see that they're building here. There's some worker nodes that are coming on. They're not quite ready yet. Let's have a look and see. They're probably been built, but they're not. They're still tainted. Yeah, they're coming up. Let's make sure we're in the right cluster. Yep, no, we weren't. So LVV48 is the cluster 2, and you can see here that we've got a 4th worker node now, and these other ones are coming online. So pretty soon we're going to have 10 worker nodes being available. At the moment there's 7, 8, yeah. So in a moment we're going to have 10, and you can see them being built in the Openshift UI behind me. So now is a great opportunity to then make use of that resource now, and instead of having 3 Hello pods running, I'll scale that up now, and because we've got the extra resources, the extra worker nodes, the GSLB is pointing most of our traffic into this node, we can now take on and scale the application up. So you can see here that I've scaled up OCP or Hello Kubernetes in OCP02, and if we have a look at that now in the UI after all those changes, you can see there's a whole raft of pods that are coming up online. So if we do have a look at the pod count, yep, our application has scaled right up, and corresponding to that UI view there, you can start to see all the node ports and node port locals. So we're still strafing traffic into all these different worker nodes now. There's 10 worker nodes that you can see. They seem to be pretty much all up. Let's check that they're all up. Yep, 10. They should all be in a ready state. Yeah, and you can see here that all the worker nodes are. Well, that guy's a straggler. Here we go. We're all up. So we've scaled up the cluster. We've protected the cluster from the inside out. We've got all sorts of automation happening against the DNS, against the IPAM, against vCenter. So it's a completely automated deployment that can all be driven from YAML programmatically via the developers. But yet all the profiles that we've consumed out of AVI have been put in place ahead of time by infrastructure engineers that know infrastructure. So if we wanted to, we could come into here and then do a scale out if we so choose to. And of course, our GSLB is still directing us into one of the 2 clusters. And in this instance, we've been directed to OCP1. You can start to see our digs are going back and forth between the 2 clusters. So here you can see GSLB sending traffic into the cluster. So that's our deployment taken care of. We can scale this stuff back in now. If I go into cluster 2, I'll scale in turn the GSLB back to 50/50. I'll scale the front end of the Hello application back to 3 replicas. I will turn the machine set back down to 3 worker nodes. And you can see here that everything is just scaling back in. Scheduling disabled on some of these worker nodes. You can see the scaling already happening. AVI has taken the back end member pool down because of the scaling from 30 nodes to 3. If I go back in and check that and re-show you that stuff again. That guy there, that was 30 before. They're all been invalidated, draining off connections, and then back to 3 worker nodes as those things come down and are deleted out of the cluster. And that's it. So hopefully that was informative. You've seen me deploy 2 applications and leverage the automated capabilities of AVI through a whole raft of IP services, DNS, IPAM, cloud connectivity, or cloud connected connectivity, all against Openshift with AVI's AKO and AMKO for MultiCluster as well. Thanks for listening.